Hello everyone, we're back on CodeForces. You guys really liked my previous CodeForces Division 4 round, which I recorded. I usually don't record a CodeForces round because I want to give my best at them, and recording is a bit hard because you have to commentate and do things. But here is unofficially now on Division 3. And we will try to, we solved all the problems on Division 4, we'll try to do the same here as well, but I don't guarantee, of course, that. So there will be explanations at the end of the video, as well as while I'm solving the problems. I will be showing my thought process, and I usually record these just for archival purposes, but you guys enjoy it as well to watch, and maybe to see how different I came up with maybe different solutions. Also I post these videos after the contest has ended. This is because so there's no cheating. Of course, there on CodeForces, like, it's more and more like I just read these blogs of like cheating and that's I mean, guys, if you like, if you do this kind of thing with like sharing solutions while the contest is going on, I mean, you have to stop, or otherwise I think everyone should be banned that has cheated, and this should be much stronger, stricter. But yeah, okay, so let's go. So decide to melody. Let's represent the melody as a sequence of notes. What is not experienced playing the guitar and can only record exactly 2 notes at a time. We'll add once to obtain the melody S, and to do so he can merge recorded melodies together. In this case, the last sound of the first melody must match the first sound of the second melody. If Vlad recorded melodies A, B, and B, A, he can merge together and okay, determine the minimum number of melodies consisting of 2 notes that he needs to record and obtain melody this. So okay, so I'm thinking about, like, okay, if it's repeating, if I have like one character which is so for each, like, you need to have at least one, but for each so maybe I will zoom in. So the answer is at least one, of course, but I will go through this, and if S is equal to Si minus 1, then I can continue making it, but I can't continue, can I? Yeah, I can continue. But also it says, like, I can record one melody and then I can merge them together many times. Okay, so actually I was wrong. I think the solution is just take the, like, make a set of strings, and you put into the set of the strings, you insert as the substring from the position I2, and then you just want to see out the size of the set. I think that's what he wants. I will explain it later. Let me just, if I understood the problem correctly. I usually misunderstand problems, but okay, I accept it. Okay, you're given an array A containing the weather forecast for the last n days. AI is the estimated air temperature on day I. You're also given array B, the air temperature that was actually present on each of days. Okay, however, all values in array B are mixed up. Determine which day was which temperature if you know that the weather never differs by more than k degrees. For example, okay, so okay, so we can sort both of the arrays. What should be written here? What should be the output? On separate line for each output and numbers the values of air temperature on each days in the correct order. So we like read, but wait, then why k? I don't kind of get it why k is needed. Okay, so let me sort all of these. Let me see if I sort them. I'll just read A and B. I don't frankly get why we need K, to be honest. So I will sort them with like indices. Then I need to say that, okay, we'll go for each of the n days in B and match that day. So if I have some answer here, and I say that B answer at A at I dot second, or is B at I dot first. And K we read, and K we read. I mean, this should work. I have no clue why why K is needed. Okay, gets accepted. Whatever. Vlad was given an array A of n integers. Now he wants to build a beautiful array B of length n. Vlad considers the array beautiful if all the numbers in it are positive and have the same parity. That is, all numbers beautiful are greater than 0. Okay. And note that array B, Vlad can assign each bi to either AI or AI minus AJ from any J. So he can like decrease some something from AI. To avoid trying to do the impossible, but as to determine whether it's possible to build. Whether it is possible. So, okay, so first the parity. We have to get rid of the parity issue. So the beautiful array, it is either all odd or all even, which means that if it's all odd, we will have to see that if a number is like even, we have to decrease it by an odd number, which means that there has to be an odd number smaller than it. If so, it's like just a simple just simple if statements. So it's let's say odd is like 1, even is 1, and then the answer will be like either it's like odd or even. Either way, if we can achieve both of them, we will say yes, otherwise we will say no. And now how to check if we can achieve them? We can iterate over all of the things, and if AI is like odd number, if AI is an even number, we need to actually say that like odd, and is there a smaller number than AI? So how do you check if it's like a smaller number? We could just sort the array. Not to use like data structures. Bool is smaller even, is smaller odd, is smaller even. Also, we need to make them unique numbers. How it was like A.3 size. There was a way how to make them unique, but also I can make a set. I can make a set, and then I could say A.insert x, which should be fast enough. And then I could say like for auto element in A, if it's element divisible by 1 and then is smaller, that's even true. And then here odd, okay, if element is this, then if element is will there be negative numbers? No. So okay, so let's say this, if it's smaller, so yeah, odd. So okay, we didn't really need to do that, but whatever. Odd is smaller odd. So if we want to make it odd, we need to make smaller odd. Else is smaller odd true. And even is if there is smaller. If it's an even number and we want if it's like an odd number and we want to make it an even number, we need to a smaller odd. Okay, passes this. Let me just submit it. Should be okay. Accepted. Okay, let's go here. Okay, let's see the standings for. Okay, not bad. Also, not good, but whatever. You are. How it was like the Chernobyl, not great, not terrible. Let me just get light here. Okay, so you're given permutation of length n. A permutation is an array consisting of n distinct integers. For example, this is a permutation, whatever, blah blah blah. To the permutation p, you need to apply the following operation exactly once. Choose a segment LR and reverse it. The reversing the segment means this, okay, blah blah blah. Then you swap the prefix and the suffix. So you swap this and this, and then okay, you'll be shown that this is the maximum possible. So okay, you need to output the lexicographically maximum permutation that can be obtained by applying the described operation once. Okay, so you have to know first. Okay, so it goes into 2000, but okay, so if we want to make the maximum possible lexicographical permutation, we want to make the 5, the n, the beginning of the permutation. If we could achieve this, it's already very good. Okay, so there will be some like places that we need to take account. So it's a bit more like logical approach, but let's see. So let me just draw here. So we have like some permutation. You need to swap some continuous sequence. So you can just choose like one and swap. Like you can do this, and then like this and this will be swapped. So what happens? It happens that this should go here, then this, and then this. Okay, so what if we choose here? This will go here, then this, then this. Okay, so let me see. Like first you have some permutation. Okay. So what you want to do is you want always to the L position, the right position will be always one against this here. The L position will be always so the right position. Yeah, because this has to be the first element, so this is the right position. Now the L position is now if I had this, it makes sense to. Does it make sense? Does it ever make sense to swap this? Okay, so we know that the right position is here, then this would be the first. So there would be some sequences as the first element. Then I want to know if there could be the. Okay, so the L has to be the second biggest element, which is on the left from the 5. Actually, no. We want L to be. This is right. If this is L, then like swap this and then no. So we could just do LNR, like swap this element and then this thing here holds. Okay, so let's try this for this permutation. 3, 1, 5, 4. So I claim, like, if I do LNR here, what will happen is will happen 5, 4, and then will happen like 1, and then will happen 2 and 3, which is not the maximum permutation, since 2 and 3 can also be swapped. This is done by saying that, okay, if I swap this element, which is bigger than this element here, so if I take this, this element would be like to the last. But wait, wouldn't this give, this gives me 1, 3. So let's, okay, so, okay, this gives me 1, 3. So we want to say that this is the biggest. So we find this L position. How do we find this R position? What do we need to print? We need to print this permutation. We need to print the new permutation. And I thought, but like scrap from my permutation that. Okay, so let me see here. And also there is this case of like being maximum permutation here, 5, 2, 3, 1. Being a maximum permutation, we want to apply as minimum operation as possible here. And what is the applyment here in the third example? The segment is 1, 1, thus making this 3, 2, 1, 4. Okay, so this is like R. So if it's like, if the maximum number is here, then we need like just to switch the maximum number. What happens if this is the case? Can we rotate something like this? Yeah, so we need to rotate, okay, so if so let me just do this. Okay, there is a little bit of if cases here. It should be if a of 0 is equal to n, then this is a special case, and you have to rotate from here to the right position of the most biggest element. So we're gonna go against like this. If a of I is equal to n minus 1, then we need to take the right position is I minus 1. So the left position is 0. Right position is I minus 1. Okay, so this is like a special case. Otherwise, we know that we have to find what is the right position. Yes. We have to find, okay, so let's solve this case. You find this right position, then this is my right position here. My left position is, what is my left position now? Here is the the trick. What is my left position? My left position would be as far let me so I find like this is the end. Think this is my right position. Now we want to swap. Maybe do this 4 and 2. Now if I swap these two, so this would be my end. This would certainly be like this, 6, 3. Then my right position will go 5. 5 to 4, or you could do, yeah, you want to swap until, what about like it was here 5, 2, then you want to swap until my second best, or no? So there's like, if this is the second best, then we want to, then we're gonna swap this, then we're gonna get this position, or if I swap this, I will get to 5, 4. So if I include this number, I will get a bigger permutation. And now when to include a number, when to not include a number. Okay, we'll definitely want to definitely include until, so we want to start from the right position, go to 0, and if I notice a number that is smaller or equal to the a of I, then I need to flip a number which is L is like minimum of R and I plus 1. Then I will reverse A begin plus L, A end plus R. I will reverse this segment, then I will go from R plus 1 till the end. I will see out this, then I will go from the 0 to R. This way I reverse the Oh, not end, begin. Wait, I got a better permutation here. Wait, what? What are L? One and two. I reverse this and it goes like 1, 3, then like goes 5, 4, and then yeah, I need 5, 4, then I need to print from L to R. Then do I ever print from 0 to L? I print them differently. Wait, what? L 2 1 2, this is reversed. 1 2, then it's like 5 4, 1 2. Wait, it should be 1 2, right? Okay, 1 2, begin R, begin L. So 1 and 2 are reversed. Can I just do this? Okay, so this is not correct. Let me just look at an easy example like this here. Always look at these examples, 4, 2, 1, 3, then like the 7th example is 6th example. Is this the 6th example? 4, 4. 4, 4. I see here. So 4, then so he reverses this and then he goes like that. I see. Well, we could technically always do that, right? Get the second biggest and reverse this. Is this the case? Result here. 4. Oh, no, not really, right? Here there will be it's a bad problem, I would say. Let me just let me maybe go on E. These problems are kind of bad, but whatever. And people came to the festival and decided to dance a few round of dances. There are at least 2 people in the round dance, and each person has exactly 2 neighbors. If there are 2 people in the round dance, okay, you decided to find out exactly how many dances there were, but each participant remembered exactly 1 neighbor. Your task is to determine what's the minimum and maximum number of round ends that could be. Example, if there are 6 people at the holiday and the number of the neighbors they remembered equal. This is your number is 1. Maximum is but each participant of the holiday remembered exactly 1 neighbor. I see. So it's like so it's like the cycles in the permutation, no? What is the minimum number? That sounds like a good problem. Problem F. This doesn't sound good problem as well, but problem G. Has a pet chinchilla, a tree of inverses and huge scissors. A tree is okay connected. I like to play on branches. A branch is a tree of 3 vertices. Okay, a cut is the removal of some not yet cut edge in the tree. He has plenty of free time, so she can afford to make enough cuts so that the tree splits into branches. In other words, after several, possibly 0, after several, possibly 0 cuts, each vertex belongs to exactly 1 branch. Okay, that seems help. Choose the edges to be cut or tell that this is impossible. That kind of seems like dynamic programming, you know? Why is this 0 here? Oh, it's already a branch. Okay. So if I cut this edge, this has to be part of the branch. Then I have to somehow know to propagate the DP. Not only that I need to cut it, I need to know. Does it need the minimum number of cuts or what? It's just like, okay, yeah. So this has to be like in some branch. This has to be in some other branch. Okay. If there's like 3, then you can't do it because this. But if there's like that, then you can merge them together if here is. I think this is a doable problem, but still I need to solve D. solve D and then we'll go in G. Maybe. I don't know. I don't know. G seems like just a math, like something for fifth cases. And F I didn't even read it, but doesn't seem that bad. So like if it's like official stats, really small amount of people, so and it's probably like masters. Okay. So okay, so what's the D? What's the D here? What's the point here? How do you find this edge? So if I have like L from L to R, this number will come to here. I have some other here which will go on the end, so this number will go after the L, and this number here will go as the first number. So I need to know this. If I cut it here on the L, on the R, going this is the first number. What's the most optimal position I can cut L to? This is this has to be greedily chosen. So R has to be chosen in the end position. This is like the end position. Then this is R. This has to be chosen. Then this here will be okay. So N, you have something which I don't care about. Then you have R. Then you have this array. So when do we want to stop? We want to stop when this number is bigger than whatever this number is. So we want to swap it exactly there where L, I want to stop it exactly there where L, no, exactly, wait, R will become, wait, there will be like N, then there will be like R, there here will be L, and then here will be this number. So we want to include L if L is bigger than this number. So this should be correct. Okay, so this is correct. This case is not correct because 9 is at front. So this is the special case, it's not correct, I think. So when 9 is at front, when 9 is on the back side, we can swap. Okay, so the second case is what? 9 should be true. This. Okay. So yeah, 9 is up in the front, so this is not a special case. This is here. If I choose this here, if I choose any of this here, there will be this. But I may want to choose 9, 9 in order to have this. So if this is the, so there's this case, if A back is N, then okay, so let's say this, else if A back is N, okay, if LA back is n, then we need to choose L is like n minus 1 and R is n minus 1. Okay, this is now fixed. This is fixed. This is not fixed again. Here is again this, then you have to how is this now? How is this even the case here? 1, 2, 3, 4. For example, the segment 1, 2 should be chosen. Oh no, the fifth example is 5, 6 should be chosen. So this is like, this is like, okay, if I have if it's on the end, I can choose as well as like okay, so if it's on the end, I need to go R will be this, but for left I need to go from R where this is the case, where the AI from, if AI is smaller than these two cases. Okay, so we have like 10 is at the front, so this is when this is the front, is this case. Then what do we need to choose? We need to choose until one, two, three, four, five, six, 7. Five should be chosen. There has to be an interesting way to do this without these many edge cases. Okay. I should be chosen. This is the first, and like they choose so 3 and 4, 2 and 1, so they choose 4, 4. No, they not choose 4, 4, they choose 1, 1. Wait, but they choose this and this. So there's like 3, and there's 4, 2, 1. 4. Can they choose like an empty thing? Wait, is that an empty thing chosen here? You need to choose L and R and reverse it. Choose the whole thing and reverse it. I don't get how, what did they choose here? Expected output is 3, which means 3 is the first guy. Means this is the R. And if this is swapped, this has to be swapped. This is R. I don't get it. Is it 3 chosen first? Then this. Aha, 3 is chosen. Okay, so that's, if that's the special case, we find L minus 1 and we say this, we can swap it, or when do we don't want to swap it? If R is n minus 1, something like this. here this is not correct. Wait, this shouldn't have any influence over this, right? No. It means that this here is not correct. It means this is not correct. It means that, okay, so we find this. And the first case is we swap, first example is we swap this and this. So we get maybe we don't want this. If AI is smaller than AG. This is R minus 1. I will submit this even though I'm not really sure 100%. Okay, gets accepted. Okay, whatever. That took me a while. And people came to the festival. So this I think is some kind of permutation thing, right? Like, what if I built a graph where, okay, you get this like graph. What happens with what is this now? 1, 2. Oh, this is the minimum and the maximum number. Okay, so let's get this graph. Let's say this here. Can copy it out. I can make it bigger. So 2 has 3. 3 has definitely 1, right? No. 2 has 1 has 2. As far as I understand this, right? Okay, 1, 2, 3, 4, 5, 6. 1, 3 has 1. So 2 has 3. 3 has 1. And now you have like another component here. 5. 4 has 5. 5 has 6. 6 has 4. So you have like 2 cycles. Okay, well, let's build this thing. So this 2. Okay. So 2 and 1 are connected. 3 and 4 are connected. And 5 and 6 are connected. But they say it could be a chain of like this, then like this, then this, and then this. So we want to know how many nodes are such that you have node X, you have node Y, and both of them are connected. Okay, so there are some cycles which we will take care, but there is also this kind. Like this is like the minimum, but when I have this kind of things, I know that I can connect them using like, yeah. So is that simple? Okay, let's. So we want to know how many permutations have we had, how many cycles we have, and cycles of length 2. So let's just length 2. Cycles plus and 2. And then the minimum number is, see how the minimum number is like cycles plus if length 2 is like bigger than 0, and the maximum number is cycles plus length. Minimum number is cycles visit at I, visit I, true. Oh, there's definitely 4 cycles. So visit at I, if it's not visit at I, we visit this. Oh yeah, like if visit at I, visited at, so like while true, visit true. this is correct. Where's the break? Where's the true? Then we go here and pass where's the t. There are 3 cycles. The maximum number is cycles minus length 2 plus this. And the maximum number is like all of them. Here there could be less cycles. Okay, let's oh, this is yeah, this is not really a permutation. I forgot about that. Okay, let's draw this. I totally forgot about this. One, two, three, four, five, six, 7, 8, 9. So 1 is with 2 a neighbor, 2 is with 3 a neighbor, 3 is with 2 a neighbor, like this. 4 is with 5 a neighbor, 4 with 5 a neighbor, 5 is with 6 a neighbor, 6 is with 5 a neighbor. Okay, then 7 is with 8 a neighbor, 8 is with 9 a neighbor, 9 is with 8. And now they say that the minimum thing is 3. The minimum thing is 1. Is that like I can join this probably? Then I can join so I don't need actually like cycles and permutations as far as I see. I need like edges. It is graphs, and then if one graph has what if you have like this something, so you have like 5, say 6, say 6, this 6, 5 and 5, 7. Now this here edge is useless because we can't use it. So we make these graphs, we build the graph, and then after the graph is built, we need to see which edges have multiple this, we need to know the number of components that are free. So I can implement like a BFS here. So there are like int components, int free components, and this is like components. The minimum number of components is that if I connect all of the free components, and the maximum number of components is components. Now, how do we know? Okay, so the trick here is that okay, we need to know how many edges does this component have to here, to some other component. So we go, maybe instead of vectors I can use a map here, and I can say this plus plus and then I will say the following for auto element in adjacency of t. So in the adjacency of t, then we want if element dot second is 2. So if there are 2 edges to t, we want to know that if t is actually like a free, if adjacency at t dot size is 1, then this is a free component. Free plus equal free component. Okay, so if it's like size of 1, then this is like a free component. Otherwise, this is like no free component. But either way, if visited at el dot first continue, else bff dot push el dot first visited at el dot first. This should work. Okay, passes. Submit. Accepted. Okay, now we have this and this problem to solve for an hour. Okay. So okay, let's read it. Ira loves. Is the microphone still working? Okay, still working. Ira loves Spanish flamenco dance very much. She decided to start her own dance studio, found any students, the ith of whom has level AI. Ira can choose several of her students to start dance with them. So she can set a huge number of dances, but she only is interested in magnificent dances. The dance is called magnificent if the following is true. Exactly M students participate in the dance. Levels of all dancers are pairwise distinct. Levels of any two dancers have an absolute difference strictly less than M. So the dancers are kinda like are pairwise distinct, but they are squished. Okay. Yes, Ira help Ira count the number of magnificent dances that she can set, since the number can be very large. Build modulo. Two dances are considered different if the sets of participants is different. So AI goes to like 10 to the 9. But we could potentially like because M goes to 10 to the 5, we could potentially somehow squish them, or like clusterize them maybe. So first of all, what we can do is of course sort them. Second of all, what we can do is, I'm a little bit hungry right now, but like it's weird. It's been like an hour and like I'm hungry, so okay, whatever. Okay, so there's N and M. I was thinking like you could maybe somehow squish them and then use dynamic programming on that. Just say standings. 400th place, not bad. Okay. Magnificent dances that can be set. So we only care about the minimum and the maximum student in that dance, right? Because the difference between the minimum and the maximum student actually is what makes it. So if I have something, if I have some array which is sorted, if I choose that this is a student in the dance, then I can choose that, let's say this is the minimum student. So there are some students in that dance which absolute values will be all here, and now pairwise distinct will be like, okay, how many of these are pairwise distinct here? Not really, right? Like, okay, so we have like some, let's say that we have some equal students here. Okay, exactly M students participate in the dance and strictly less than M. So, okay, we have something here. And let's say that we could choose, okay, so we have some students, let's call this left. We have to the left side some students. This like 1, 2, 3, 4, 5. We know how this is the big problem here, like the pairwise distinction here between these three students. Okay. Okay, so if I have pairwise distinction, can I say that, okay, this is like 2 to the 3 ways to choose like a subset of them, but we need to choose something to end. So this is apparently, this is, so we can binary search where this point is. This point we can easily binary search. But after binary searching where this point is no longer clear. Okay, one thing is the linearity, because m here is equal, like let's say m is 5 here, right? Now 5 students will be at least here. If there are multiple, now we know that on this graph we will have, like we will choose let's say we will choose 5 students, and if there are multiple, like here, multiple students, we will choose these 5 students, of course, and then from like the pairwise distinction we can okay, so how many students, how do you compute this? So you have some number. How do I compute this? I can switch times 2 here, I can switch times 3 here. So I need some range, I need some range product. I have 2 students here, I have 3 students here, I have 1 student here and 1 student here and 1 student here. So from here I need some range product. So okay. Okay, so we already have this. So I need some range product. I need the product of this value times this value. Let me just fix something here. I have to fix this snippet, but whatever. I have them hard coded some values here. Okay. Okay, we will go and we will use the modular non-int. So this is another modular. Let me here change this. Value, blah, 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 blah. Okay, so we have like this AI, right? Like, I think this should kind of work. So for each set, we need at least we need to compress these integers, right? need to compress these integers. I mean, I don't know why I did this. I could do this. I could sort them, then I could have another vector, which is just a copy. Then AI is lower bound in the compression thing, begin. And then this is AI, then minus function begin. Okay, then you would want to say, okay, so we compress them. Now in the segment tree, we want to say that, okay, so we have some seg tree. I want to say that put in this A of I plus 1. So I'll just change my here. I'll change this. Okay, so I put there plus 1. Then I need to go for each of the, so from M dancers up to M. Is it M minus 1 dancers? Then we need to binary search. And we say that, okay, if at L is, so say from 0 to L, if okay, if we need to also I didn't even need a second tree because I can divide that by the inverse, but whatever. I also want like prefix. Then I want to go through all the prefixes. do this. Then what I want is like the prefix of I minus the prefix of mid. So this is like the other point minus 1. So like this is like how many here are this prefix of mid. If mid is this, otherwise it's like 0. So how many in this? If many is bigger or equal to if many is bigger or equal to if many is smaller, then I need to move the right smaller than m, then I need to move the right pointer to the mid, otherwise I need to move the left pointer to the mid. And now here I will print out LNR. And now here that's okay. And now I need in the tree to ask from L to R plus 1 or R. I need to ask for the value in that tree, and actually because of the compression we need the compression to be here. So how do we take account of the compression? How much we can go back? So essentially, instead of we don't even need this. We could do this. We could do this. Let's say L is like this. L is this lower bound of comp begin, not compression, comp begin, comp end of AI minus M. This is the lower bound minus comp begin. So this is the lower bound. We find this value, and if I minus L plus bigger than M, then we find this and we say answer plus V, something like that. First I need to say where this L is to see. on calculating. Right, let me print. Let me print this. Okay. We have this. Now this goes to -1. Lower bound of AI. Oh, not AI. Comp I. Okay, 4. Now 4 is only possible if I have this 4 here. Right, so L is fine. Right, this is possible multiple times. Minus L plus 1 is bigger or equal to M. Okay, 3 ask value. Oh, yeah, so, yeah, okay, so I have to, like, is that the question? I think so. I have to do 1. I mean, 1 because it's like, it's multiplication here by default is 1. And yeah, this should be okay. Now, I'm so hungry. I don't know if I could finish the other task, but whatever. This is definitely not integration. Oh yeah, so here if the value is yeah. We need here to get 7, which is not correct, but we'll fix it. So is that correct? That's correct. I think that's correct. So now lower bound is 0. We can take all of these elements. M in our case is 3, so it's like 3 and 0, then this is like 1. The result is 1. 1 is what? 7, 6. Okay, that's 1. There's like 2. There's the first test case magnificent dances are this. Okay, let's sort the first test case because that doesn't give us a lot to go forward. What I can do is I can just print okay, so if I have 11, then -4 it's 7. So I have to, from here to here, I have to oh, actually not -4, minus minus n plus 1 or something. So I have like 2 here. 10 is like -4. Plus 1 is like 1. That's 2, that's 1, that's 2, 2, 2. 11. In the 11th case we have 2 of them. In the 10th case we have 2. So in the 11th case, in the 10th case we have 2. Here we have absolute difference strictly less than m. Strictly less than m. In the 0th case we have 6, 7, 8, 9, which is 1. 6, 7, 8, 9. Is there a case 6, 7, 8, 9? There is a case. Then we have with 10 here. Oh yeah, so if ai is ai minus 1, I is bigger than m plus 1 and ai, this we want to continue here. I think we need to do this. Still some overcounting happens. Here where 0 is the case, let me see. Why is this 0? Oh, pairwise distinct, yes. Oh. Yeah. I minus L is this, but we need like the pairwise distinct things. Yeah, so we need like another array where you will say that like this is pairwise distinct. Not only that I need to do this, I also need to do that the prefix of I minus the prefix of L this is what I need to do. Wait, I need to print the prefixes, see if that's correct. 1, 2, 3, 4, 5, 5, 6, okay. Prefix I minus 3, 3, 4, 3, 5, 6. Okay, that sounds correct. Let's see, it's correct. Now we only need prefixes, to be honest, because so prefix is like L. L is the lower bound. So this is, okay, so what is L here? What is I and what is L? I is 3, 0, 1, 2, 3. Here, okay, so just see where it fails. Oh. Okay, 0, 3 fails. Why? Why? Why does it fail? This is 0, prefix at I should be 4. 4. Four minus okay. 10, 0, 5, 11, 1, 2, 1. Seems like it's working. Okay, let's submit it. Yes, accepted. Okay, now it's just G. Now it's just G. Okay. And then we'll go eat because I'm hungry. Okay, so G is like a tree connected without, okay, so you have like a tree and then you have these branches, and is it possible to do this? Now this should be a greedy strategy on how you remove them, because as far as I see, if there's like one this here, like you start probably go DFS and then you start here and you try to remove this, right? If there's only one, then this is removed and automatically this is removed. But then now there could be like an even number of things, and then you would remove. Yeah, so I think it should be just DFS. I'm not sure why. There are checks here. There are checks. This is not, even though it looks like an easy problem, I don't really believe it. I'm so hungry. Okay, and then you kind of wanna. It doesn't really matter where from your DFS, right? Does it? I don't think it matters where from your DFS. I think it does matter. There won't be like void, there will be something like integer, I don't know. So there would be something like, let's say that one I don't know, let's say that one means that like it's done. Then there would be, okay, so if DFS 0 0, then cout answer.size for pair for you and the answer cout you, there will be like this lcout -1. Now of course there would be like an answer array. Okay. And then so there will be answer array, and then this is cut, or we can't do it. And then okay, so what happens if the adjacency of the vertex is 1? So if adjacency at u.size is 1, it means like it's a leaf. What happens in this case? But we could start at the leaf node for some reason, right? Do we want to start at the leaf node, or do we want to find a node which is not a leaf node? Yeah, let's find a node which is not a leaf node. So let's go int, let's say root, then let's go over n if adjacency at i.size is bigger than 1, root is I, break, and then we say root. Okay, and then what we say is does the edge have to does the edges have to be in the same order? Yeah, whatever, it doesn't matter. We'll see. What is this now? Like, okay, 2 edges. So you need to print which edges you need to cut. Okay. Edge here. Wait. Okay, so this is the case. So if it's a leaf node, so we know that the root will never be a leaf node. Okay. Let's say this is a leaf node. Then I need to make this happen. So I need to include it. So I will return 0. Need to include this node. Okay, so if I will go like DFS. And then I need every DFS will return something. And I need to count how many nodes should I include. Not included. If return is 0, not included plus plus. Okay, so not included plus plus. This means that I'm now in some other node that has some children, and some of the children are not included. Actually, no, I can't even include more than like 2 children, right? So like if I have like 3, can I even do it? Can I ever do it? Is the question. I can do it. Like I can cut all of these. I can at most include, so I have like some children, right? I need to cut it. If I have some children here and I say, okay, this is not included. Now I come here. Now I say this must be included in the other. So if adjacency to dot size is equal to 2, and if not included is bigger than 0. So if it's not included, I have to be included in you. This means that I will return 2. And if it's returned 2, then there is like half is on. So if this is the case, I have to be included in you. What if the size is 2 and like, okay, I have something here. right? And then I need to cut here. Okay, size is 2. So what children should I cut? Children should I cut? Is my question. I should cut children that return that they are fully included. If return is 1, cut it. Push back E. So we cut it if it's 1. If it's not included, so if it's 1. Also here, if it's like 1, I have to include you, so I have. What children should I cut? I would cut these children. What other children should I cut? So I cut all of them are that included. So this is like that. Let me just imagine another case where, let me just check these cases out. So if I have, so this guy will say return 0 because it's size 1. This guy will say, okay, it's not included, but this guy has size 2. And it's not included that I have to be included. So this guy says 1, and then this guy, as soon as like it has to be included. So okay, if it's not included, else if there is a guy that have to be included, then I will return 1 as I am included. Okay, now what else? There is a thing. If I have to include 1, then I need to cut everybody else which is not being cut. So let's just do this. If there's this, then I have to cut everybody else. So half is -1, half is v. I have to have v. So if it's half, it's not -1. If it's not -1, then I have to cut everybody else. If half is v, then I will continue. Now if there is no vertex like this, then I will choose 2 vertices that I have not cut. Not included. So now there's no included. So if it's not included, there's like not included and there's included. Not included. Now we say this: if not included is 1, then I will okay, so what is this here? If I have something that should be included, then I cut everything else out. Then I return that I have been successfully now there should be like an OK function. OK is true. Set OK is true. Okay, so now the thing is this: if I have something else and I need to see if when I cut these I don't have multiple included. Okay, so I will do this. Returns. If I have multiple tools, I can't do it. False, and then like I will return if frequency of 2 are bigger than like 1, then OK is false. Turn 0. If frequency of so not included, this is 0. So frequency of not included. Okay, so this is what other children should I cut. Then I cut these children. Okay, then answer pushback. How many? 6 minutes. We'll try to solve this. Okay, so answer insert V. Then return 1. Okay. If there is, I should have you then continue. Okay, done. Okay. Okay, not included. So if not included is 1 is not included, then I would cut. If 1 is not included, what if there are 2 not included? Then I need to say if there are multiple, if frequency of not included is bigger or equal than 3, so it's bigger than or equal than 2, then it's okay, false. If it's not included 1, then I have to include this. And if it's not included 2, then I have to include both of these. Answer clear, n minus 1. Okay. Okay, why doesn't it come to here? Four minutes to debug stupid things. UV, and minus 1. What's going on? What's going on here? Oh, what? Oh, this is so bad. JCC answer. One, 0, 1, 2, 3, 4, 5, 6, 7. What's going on? Don't kid. Stop kidding me, man. Am I crazy or something? Am I crazy? I don't think I don't understand. Clear, resize, clear. I don't understand this. What's going on? Am I that crazy? What is going on? This is the most weirdest thing I have ever seen. Cannot understand this. I'm baffled. I'm totally baffled. I'm totally baffled. I can't understand how this is. What's going on? Is it like due to this? I mean, it's I don't understand it. Is it resize isn't no reserve is something else. Then resize is something else. Because reserve doesn't necessarily resize. Wait. Into V, right? Okay, adjacency at U. Push back V and I plus 1. Adjacency at V. Push back U plus 1. Name clear, name resize. No, it doesn't. What does it maybe affect some like? No, it's only this. It's like only this. I'm baffled. Don't I see something? This works, and then adjacencies. Now it works. What's the idea? It crashes somewhere else. Okay, so it goes up to here and it crashes somewhere else. Okay. Now we can... Okay, if v is the parent, continue also here. Well, that's not right. That is definitely not right, but okay, now I'll fix the crash. Okay, so whatever, we'll fix. I'll fix that off stream. Okay, so okay, let's go over each task so we can yeah, finish. Okay, so first of all, musical puzzle. Musical puzzle was a task which just, what you needed to do is, if there is this many times in the word, you can reuse it. This substring of 2 letters. So you go over all of the substrings of 2 letters and you insert them in some set, and then you see the size of the set. So this works in nloc and time because the substring is only 2. Okay, that's problem A. Problem B. You had some array and you need to restore some values such that they are most closely resemble this array. But the problem is that like k here doesn't really affect anything. It's just, they don't say that it is impossible to do this. It will be always possible to rearrange such that the equality holds. So you just sort both of these arrays and you see like the answer array, you try to match for this b, for the smallest b, you try to match to where the smallest a was. So this is the idea. The smallest b, you put it where the smallest a is. And then you do this all the time. So this works in nloc and time. Okay, let's go next. Vlad building a beautiful array. So this was, okay, so first of all, you needed to say yes or no if this is possible. You didn't need to actually like construct this array or say anything else. And in this beautiful array, all of the numbers have to be greater than 0, and there will be all even or all odd. So what you try to do is you try to construct, you try to see if an odd array can be constructed or an even array can be constructed. And when is this possible? Okay, it is possible if I order all of the elements in a set. I don't care about duplicates because each duplicate can be actually like, if you prove for this array, any array that contains duplicates, and this array is a subset of, like not a subset but like a true subset or whatever, it doesn't matter, like duplicates doesn't matter. Okay, that's what I want to say. Okay, so you clear off the duplicates and then you see, okay, if the element is an even element, you need to say, can this array be made odd? It can be if and only if there is a smaller odd element than this element, such that this element minus the smaller element, the smaller odd element, will give you an odd element. So even minus odd will give you an odd. Okay, what if the element is an odd element? Now, can we transform the array into an even array? So this element has to be transferred. In order an odd element to be transferred to an even element, it only can be, you need to subtract an odd element from it. And this can be only done if there is a smaller element than it, and it's an odd element. And when we get an even or an odd element, we say that there is a smaller element, because every element when we traverse to this array will be sorted. So the next element will be greater than any element which we have traversed through. Okay, so that's problem C. Problem D took me a long time just to like make these cases, but it's like just casework. I won't explain the problem. It just took a long time. I don't know why. It's just brute force, and it's like a simple problem. It's constructive algorithms. I personally don't like constructive algorithms, but whatever. So I mean, there could be constructive algorithms which are really good, but also constructive algorithms which are boring like this. You will see what you need to do immediately, but figuring out all these cases, it's not kind of easy. I mean, it's just painful. Okay, so round dance is like, okay, you need to say you have some special graphs, and you have to see what is the minimum number of components you can create and what is the maximum number of components you can create. Okay, so what are these special graphs? Here you have like this. You have some graphs which are made of multiple components, which can be made of multiple components, but there are like multiple edges here. There could be like 2 edges. And now any of this like multiple edge, I can, if this edge is on a leaf node and it's a multiple edge, I can redirect this edge to some other component. But if this edge is inside, so it's not on a leaf node, I cannot. So this is like I can delete it only. Like I cannot do anything with this edge. Only leaf node edges matter. And if you want to construct like the minimum number of components, you will get these leaf node edge. Each component has this leaf node edges. You will count them. And then let's say this and this have them, and then this edge can redirect to this component here. Let's say like this. And then this edge can redirect to this component. You can make these rings of components only by this, like, I call them free components. Free components is a component which has multiple edges on a leaf node. And what you do is like you just BFS. But interesting enough, the adjacency matrix here is like, because of multiple edges that like you can contain multiple edges, I made it as a map. So I count how many edges there is to like other vertices, and then I push BFS to count the components, and while I count the components, I see if there is like a multiple edge and this is a leaf node. If this is a leaf node and there is a multiple edge, then this is a free component. And then it's just like matter of mathematics, when is the minimum number of free components, so this is the component minus the free component plus 1 if the free component is bigger than 0. And this is like this is like all the components as the maximum number of components. So it's pretty easy, pretty cool problem. This is a really good problem, I would say. Okay, so F, what is F? F is also a good problem. Not that I actually needed segment tree, because like you have like module here, and you can divide, and you can like do prefix arrays without like the need of segment trees. But whatever, I solved it this way because I actually don't type segment tree, so just copy it, paste, and modify a few things. I don't need to type it. One thing you will notice in this problem is that like exactly m students and strictly less than m. And what does that mean? It means that you have some kind of like here connection between these two constraints. And the connection between these two constraints help us make this graph such that like if I have m students that are on different levels, and this level here is this level minus m plus 1, I will have for each level at least one. I need to have at least one student for each level. Okay, and because this is like exactly M student participates, this actually works. If there would be another K student participates, then this would become a lot harder problem. Okay, but because exactly M, and now there could be like two students that have like the same level, and now you can swap them, and the combinations you can create is just the product of the frequency array that actually is here. So like it's the product of how many students have this number times how many students have this number times how many students have this number times how many students have like this number, the M here or whatever. And then you just product them. So what I do here in the code, first of all, I want to compress all of the students, because like this 10 to the 9 is like really big. And I won't be able to use any prefix arrays or segment trees on 10 to the 9. But you can always compress it. So A here becomes a compressed array. And then I count if like I see another different student, I put a prefix on it. So I can count, the prefix actually allows me to count if there's enough students in this range to create a group, because sometimes there can't be enough students. Sometimes like the difference on M levels, there could be like less than M students that have this difference. So, okay. So I compress them, I count this for each number. If this is the same as the last number, I want to put it in the array, in the segment tree. Why is this? Because I already in the segment tree, by default, I already have one. So if I don't have this, I will overcount by M. So I have to like by M, but yeah, I will overcount by something. Doesn't matter. So this, okay, and now I calculate the prefixes here. I actually like just loop, like sweep it once to the prefix, and now for every index, I wanna binary search where the last compression of like this index minus M. So where can I, in what range I need to look to get at least M students that have at most difference M, because we only care about the maximum difference, which is here, and the minimum difference. So this is only this range is so where on this scale is the minimum difference? Where is this? So you lower bound, you binary search it. When you get this L, you check if there is enough students to create at least one group. If there is enough students, then you ask for the tree. In the segment tree, you ask, okay, if there is enough students, but let me see how many different combinations of these students can I create. And there will be at least one, that would be at least one. Yeah, so answer plus one. This is kind of it. E and F took me like a lot less than D, just because D is I kind of don't like it. But yeah, so G I think G is like I will fix this, but G should be greedy, should be just greedy approach. Let me just yeah, so should be greedy approach. Otherwise, yeah, really nice CodeForces. CodeForces around. We were really close on G, so I mean, also 400 place, 500 place is not bad considering my rating of 1800. And I cannot like solve faster these problems, but we solved all. We can say we solved almost all of them, right? So yeah, thank you guys so much for watching, and I see you in the next one.